Broadcast is now starting. All attendees are in listen-only mode.
Welcome everybody to Synthetic Sapphire Properties, Use, and Selection, a webinar presented by IRD Glass and hosted by Photonics Media. My name is Robin Riley and I'm the Photonics Media web editor. Our speaker today is Michelle DeCastro, National Sales Manager for IRD Glass. Michelle will be speaking today on synthetic sapphire properties, applications, grades, manufacturing, and special considerations for its use. If you have any technical issues during this webinar, please log out and log back in to rejoin. A recording of the webinar will be available on the Photonics Media website shortly after the presentation. We encourage you to ask questions throughout Michelle's presentation. Just type your question in the question box and we will answer as many as possible at the end of the session. And before we begin, we are going to ask attendees a quick poll question. And so the question is, for what applications are you considering Sapphire? Please choose all that apply. The possible choices are medical, laser, defense and aerospace, industrial, or commercial. I'll give you a few more seconds before I close this poll and share the results. Okay, I'm going to close the poll and share the results. And there you see. And I'm going to hide the poll. And now I am going to turn the presentation over to our speaker, Michelle DeCastro.
Thank you for the introduction, Robin, and thank you all for joining us. As Robin said, today we'll be talking about synthetic sapphire and why it's used. If you're not familiar with synthetic sapphire, you probably think of the blue or pink jewels of natural sapphire. Sapphire can also be synthetically grown to give it higher purity and colorless clarity. Just like we don't use lava, which is actually natural glass, we will be strictly discussing synthetic sapphire today. I was inspired to make this presentation because it seems like sapphire has become a bit of a buzzword. People will ask me if sapphire would be a good miracle glass replacement for their project without even knowing what it is. We can probably thank the marketing geniuses at Apple for that. 5 or 10 years ago, I saw the same thing with Gorilla Glass. Just like Gorilla Glass is not the perfect glass for every application, it's important to learn more about sapphire to get the most out of its unique properties and your money. While IRD Glass does not grow synthetic sapphire crystals ourselves, we work with multiple sapphire growers to select the most suitable sapphire for our customers' applications. I hope that by the end of this presentation, you'll know that sapphire is more than just a buzzword and have more ideas about good places to use it. I also hope that a better appreciation for how sapphire is made will help you be more strategic during your design process. A little bit about our company. IRD Glass and Ceramics has been a custom component manufacturer for over 30 years. We process a variety of materials, including most glass types, ceramics, nacor, and silicon, from multiple material suppliers. As a veteran-owned small business, we've continually grown steadily through long-term partnerships with our customers, as well as strategic investments into our manufacturing capabilities. For the past few years, IRD Glass has made extensive capital investment and process developments to focus on machining and polishing sapphire windows, sapphire precision components, including sapphire laser reflector cavities and prisms. We've drawn on our long history of solving some of the most difficult manufacturing challenges in a range of materials from super hard silicon carbide to soft specialty glasses. Our customers are always pushing the boundaries of what is possible, and so are we. Although traditionally 100% custom manufacturer, this year we started a stock sapphire window program to give our customers a cost-effective, faster option for prototypes and research. If you'd like more information, please see our stock sapphire list on our website or contact me after the webinar. Check back often because we'll be adding new stock part sizes every quarter. overview of today's talk. What is sapphire? People often request sapphire glass, but there's actually no such thing as sapphire glass. So what is sapphire and how is it different than glass? Sapphire properties. We'll be going over some key properties that make sapphire unique and preferable to glass and how those properties benefit different applications. Manufacturing techniques. Sapphire is made using a variety of growing techniques, each having a strength for different applications. With consultation, your sapphire provider should be able to choose the best manufacturing method for your application. Quality grades. Like the Fused Silica webinar from last week, sapphire comes in a wide range of grades to allow you to balance price and quality to best suit your application. Application highlights. I'll be mentioning some common sapphire applications throughout the talk, but I've also selected a few additional applications to highlight. Special considerations. Fabricating and using sapphire is not the same as glass and can add difficulty to a project. We'll discuss some special considerations that fabricators and designers need to consider when making a sapphire part. So what is sapphire and how is it different than glass? We get requests all the time for sapphire glass, but actually sapphire is a crystal, not a glass. Glass is an amorphous solid. It's basically a frozen liquid. That means it doesn't have any strict crystalline structure, so all of its properties are the same in all directions. Sapphire being a crystal means you have to consider not only the properties that are important for your application, but in which orientation you'll be using it. Most glasses have the same properties in all directions. Sapphire also can't be molded, drawn, or cast to final shape or near net final shape like glass. It must be grown. You can pick a crystal growing technique that will yield the most efficient shape and do further processing from there. But even then, the processing recipe needed to yield a good finished product will depend on which way the sapphire is oriented. Because sapphire is so much harder than glass, it also requires either much higher processing pressures or production times for the same amount of work on glass. Although sapphire can be fabricated on the same equipment as glass, specialized equipment and processes need to be used for the most cost-effective manufacturing. So although sapphire can offer some really great benefits in performance, there are costs and limitations to consider. Given the additional complexity and cost of using sapphire, why would you want to use it? Most applications we see at IRD Glass take advantage of sapphire's superior strength and scratch resistance or optical performance for both optical and mechanical applications. Sapphire is the second hardest natural substance in the world, second only to diamond. For optical applications, sapphire has a broader usable wavelength transmission range than fused silica, which is already one of the broadest transmitting common glass materials. The UV and infrared cutoff wavelengths will vary depending on quality, grade, and budget for both sapphire and fused silica, but sapphire can transmit much further into the infrared than fused silica, up to about 5.5 microns. While there are other materials that can transmit further into the UV and infrared, such as calcium fluoride, barium fluoride, or magnesium fluoride, they're generally more expensive and otherwise more limiting than sapphire. Sapphire can also be used at much higher temperatures than fused silica, which is also one of the most temperature-resistant glasses available. The actual melting temperature of sapphire is above 2,000 degrees Celsius. Although the thermal expansion coefficient of sapphire is higher than fused silica, it is still very thermally shock resistant compared to other glasses and materials. This is in part due to its excellent thermal conductivity. Both sapphire and fused silica are resistant to solarization or darkening from UV radiation compared to most glasses. The degree of darkening will depend on how pure or defect-free the materials are. For those in the optics industry, you may be surprised to know that both sapphire and glass have been used as thermal conductors in completely non-optical applications. But here, sapphire really shines. It is many times more thermally conductive than fused silica. Although fused silica is one of the most chemically resistant glasses, it still has its weaknesses. For the most caustic environments, sapphire is the clear winner. For electrical applications, sapphire is a superior dielectric material with a high dielectric constant and low loss tangent. Sapphire's crystalline structure is what really sets it apart from glass. But first, let's talk about a crystal that everyone here is familiar with, ice. Solid water, or ice, is an isotropic hexagonal crystal. All of its sides are the same, and so its physical properties are the same no matter which way you look at it. That ice cube isn't going to cool your drink any faster if you flip it upside down. Sapphire is also in the hexagonal crystal family, but it's anisotropic. An anisotropic crystal has planes or sides that are different. Unlike isotropic ice, an anisotropic crystal properties depend on crystal orientation. Common sapphire orientations include C-plane, R-plane, and A-plane. C-plane or C-axis sapphire is sometimes called 0-degree sapphire. It is the most common and lowest cost orientation for optical applications. In a rod, the C-axis orientation is along its length. In a window, the C-plane is along the surface and the C-axis direction perpendicular to the face of the window. A-plane sapphire has a plane that's perpendicular to the A-axis. The A-plane is parallel to the C-axis. R-plane sapphire has a plane inclined 57 degrees to the C-plane. M-plane is parallel to the C-axis and inclined 30 degrees to the A-axis. The N-plane is inclined 61 degrees to the C-plane. I have never personally had anyone inquire about N-plane sapphire, but there's always a first time for everything. This plane is mostly used for epitaxial growth applications. Intelligent orientation of sapphire can optimize properties for a particular application. For example, many customers want to optimize for impact resistance or to eliminate birefringence. This can be done by aligning their direction of light or impact along the C-axis. In this case, C-plane sapphire would be preferred. For cost savings, sometimes people don't care about crystal orientation. In this case, a customer can request random orientation as a lower cost option. In random sapphire, the part is manufactured without concern about orientation. Random sapphire should be the default crystal choice for sapphire windows unless the application requires a specific crystal orientation. These days, C-plane sapphire is so common that we're finding that the price for optical quality C-plane raw material is almost the same as optical quality random material. R-plane, A-plane, and other orientations cost a premium from raw sapphire crystal manufacturers. Because each orientation has a different hardness and other properties, we've determined that they each require their own processing recipe for optimal fabrication and finishing. A process that makes a great cost-effective 10th wave 10.5 scratch dig window in C-plane will not work in other orientations. We've personally struggled with tight specification M-plane optical windows until we were able to develop a unique process for it. That process required higher pressures and longer processing times. Even handling different orientations can be difficult. For example, R-plane cleaves easier than C-plane. When processing or handling, this translates to a higher risk of breakage and potential yield loss. Most of the applications for sapphire we see at IRD Glass are optical, where the most suitable quality sapphire has similar pricing for both random and C-plane orientation. Therefore, we primarily use C-plane sapphire, even if a customer can use random sapphire. This allows us to have an efficient and predictable fabrication process and consistent quality results. Another reason we tend to choose C-plane over random sapphire for quality optical applications is because we've had some bad experiences with random sapphire from less reputable suppliers. The random translated to a random assortment orientations within the same piece of sapphire. Those are just impossible to get high-quality optical finish and usually end up with splotchy surfaces. So now you know that sapphire isn't as simple to use as glass because many properties depend on crystal orientation. Now we're going to go over various sapphire properties in more detail, including some applications that are benefited by each one. I'll break these down into physical or mechanical properties, optical properties, chemical and radiation stability, and thermal and electrical properties. I've included a detailed specification page for each property category for your reference. While searching sapphire material suppliers and the internet for various property specifications, I did notice that there was a difference depending on the source. Unfortunately, IRD Glass is not able to make most of these measurements ourselves, so I encourage you to contact your material supplier for the specific material properties if it is important for your application. Because I have compiled this data from many resources, there may also be some inconsistencies within this presentation. So as we just learned, the physical and mechanical properties of sapphire depend on crystal orientation. Sapphire is hard and scratch resistant in all orientations, but some are better than others. Hardness varies from 1800 newt parallel to the C-axis and 2200 newt perpendicular to the C-axis. Because of this, it's best to use C-plane sapphire in high-impact applications and pressure vessels. Sapphire's strength, combined with other properties of sapphire, make it a great material for many different applications. Sapphire is tough over a wide range of temperatures. Combined with its chemical stability, it makes it an ideal material for medical applications such as endoscopes and probe lenses, needles for thermal treatment of tuners, and scalpels. Because of sapphire's higher biological compatibility than metals and polymers, it's also useful for implants. Sapphire's hardness and strength, combined with thermal shock resistance, enables sapphire to be used where other structural materials fail, such as wear parts, nozzles, bearings, blades, tubes, and jewel bearings. Sapphire's hard, scratch-resistant surface means it can be polished to a very high flatness and smoothness for substrate applications and precision components. Sapphire can be made much thinner than BK7 glass windows. At IRD Glass, we've lapped and polished 1-inch sapphire windows down to 125 microns thick. For contrast, the thinnest equivalently sized BK7 windows we processed are over 500 microns thick. I'm sure we could make thinner parts of either material with additional development, but it certainly is easier to make a thinner part with sapphire. Sapphire's scratch resistance makes it ideal for scanner windows, protective windows, and high-end watches. You all have probably heard about Apple's plan to replace iPhone screens with sapphire for this reason. Cost unfortunately scuttled this endeavor. And one final point, the fracture strength and toughness of sapphire can be increased even more by carbon or titanium doping during the raw material manufacturing process. The optical properties of sapphire. Here's a table of optical data points for reference, but I'll show some curves that better demonstrate sapphire's optical properties. In essence, sapphire has good transmission from the UV to the mid-IR and has a higher index of refraction than fused silica and other common glasses, such as borosilicates and NBK7. The exact transmission spectrum of sapphire is going to vary slightly depending on the quality and grade of material, as you can see from the first graph. Sapphire is available in both different quality grades and different optical grades, such as UV grade and IR grade. Defects and impurities will reduce transmission in the UV. Typically, sapphire has good transmission from about 150 nanometers to 5.5 microns. At the center of the transmission window, reflection losses dominate because of sapphire's refractive index, with a surface reflection loss of about 14% at 1 micron. At the far ends of the optical transmission spectrum, absorption losses dominate over the reflection losses. Here, thickness plays a big role in transmission. Because sapphire is so strong, most applications can use a much thinner piece of sapphire than standard glass. By designing with sapphire's unique strength in mind, you can squeeze out some additional transmission from your system by reducing the material thickness. Because the raw material cost of sapphire is so high relative to the processing costs for standard optical windows, it's usually less expensive to go with a thinner sapphire window anyway. In this slide, we compare the transmission spectra of sapphire with quartz. Again, the exact UV and IR cutoff wavelengths for both materials of the same thickness are going to be determined by the grade and type of material. Sapphire can also be made thinner than fused silica for the same application to improve transmission. Overall, if you don't care about the other great properties of sapphire, and you're sticking to a wavelength range between mid-UV and near IR, then standard optical materials such as fused silica would still be your best, most cost-effective option. Sapphire is denser or heavier than most optical glasses, so it also has a higher refractive index. For example, fused silica has an index of refraction of roughly 1.5 to 1.4 versus 1.8 to 1.6 for sapphire in the same wavelength range. This also means that the percent transmission loss to surface reflection is higher for sapphire. Most of the visible and near IR light loss is actually due to reflection because materials with higher index reflect more light. For Sapphire, that's about 14% light loss at 1 micron from reflection alone. That's more than double the reflection loss for fused silica. Reflection losses can be corrected with anti-reflective coatings, index matching, or surface treatment. Sapphire birefringence is dependent on crystal orientation. There is no birefringence along the C-axis. At right angles to the C-axis, there is a weak birefringence of up to 8%. So for certain applications, C-plane sapphire or sapphire with light traveling parallel to the C-axis should be specified. The combination of high transparency across the UV to mid-IR with high chemical and temperature resistance makes sapphire an excellent choice for windows and viewport applications in high-performance vacuum systems, furnaces, deep-sea cameras, fire alarm systems, etc. Crystal orientation can be strategically chosen to manipulate birefringence for wave plate applications. Wave plates are usually made out of A-plane or M-plane cut sapphire to get the highest possible birefringence. The high refractive index of sapphire make it a suitable material for prisms and lenses. Its chemical and thermal resistance can serve in conditions that traditional optical glass materials can't. The good mid-IR transmission from 3 to 5 microns, along with superior strength, makes sapphire a choice material for mid-IR guided missile domes. Here's a chart for chemical and radiation stability of sapphire. Sapphire is insoluble to nitric acid, sulfuric acid, hydrochloric acid, and even hydrofluoric acid up to at least 300 degrees Celsius. It's resistant to alkali up to 800 degrees Celsius and resistant to metals up to 800 to 1000 degrees Celsius. This makes it a far superior material than glass for caustic environments. Sapphire is also resistant to radiation darkening. This is especially useful for UV applications where many glass materials darken significantly over time. Semiconductor wafer processing uses many caustic chemicals for processing, such as hydrofluoric acid and fluorine plasma. Combined with strength and resistance to chipping, this makes sapphire a durable wafer carrier. Broad chemical resistance also makes sapphire ideal for chemical sprays and nozzles. Sapphire's excellent chemical resistance combined with thermal resistance and optical properties make it suitable for gas exploration and viewports in caustic environments. Resistance to radiation darkening makes sapphire suitable for long-term, high optical energy applications, such as high-power laser windows and space applications. Darkening and solarization resistance can also be improved by using very high purity and low defect quality sapphire. Sapphire is a great thermal conductor. Fun experiment: if you see sapphire and glass windows on a table and can't tell them apart, you can tell which one is sapphire just by picking them up. The sapphire part will feel colder in your hand. With thermal resistance up to 1800 or 1900 degrees Celsius and high thermal conductivity, sapphire has good thermal shock resistance and can be used in many harsh process environments. For the same reason, sapphire is a great material for high-power lasers. This includes not only protective windows, but laser reflector cavities, prisms, and other laser components. The thermal conductive properties of sapphire also allow it to draw heat away from the laser system. Low expansion and high temperature resistance are great for space technology applications. Even the electrical properties of sapphire vary based on orientation. The dielectric constant varies up to 20% between axes. C-plane sapphire is a better insulator. Sapphire's high, stable dielectric constant is a good insulator for LED, RF, and microwave applications. A-plane sapphire is used for hybrid microelectronic applications requiring a uniform dielectric constant and high insulating characteristics. There are many growing methods for creating synthetic sapphire, each with their own cost and quality advantages depending on the application and material requirements. Some methods are better for optical applications, while others are better for mechanical applications. Modern commercial sapphire production essentially consists of two stages. The first stage is melting raw sapphire or alumina in a crucible or furnace. Raw sapphire consists of either powder, sintered charge, cracked crystal, or polycrystalline ingot. The second stage is cooling or solidifying and crystallizing so that all the crystals are aligned. Two main categories of commercial sapphire crystal growing are boule and drawn. Boule-grown sapphire is clear, free of seeds, bubbles, and stria, and can be machined into a wide range of shapes and windows. Sapphire drawn from a melt allows longer lengths and a wider variety of profiles, such as tubes, rods, or sheets. In general, boule-grown sapphire is of higher quality than drawn sapphire. Of course, there's a third stage of manufacturing where the raw sapphire material is processed into a final finished component, whether it's cut, lapped, or polished, or coated. But for this section, we'll focus just on the raw material manufacturing. It's good to know what method your sapphire supplier uses to grow sapphire so that you have an idea about the expected quality. Especially when buying foreign-made sapphire, the quality stated is often not what the quality you receive. Here's an overview of some common sapphire growing methods. The Verneuil flame fusion method was developed in the 1800s and is one of the first synthetic crystal growing methods still used today for cheap, low-quality applications such as jewels, gemstones, and washed windows. In the Krokowski method, or pull-from-the-melt method, a tiny sapphire seed crystal is dipped into a crucible containing molten alumina and then slowly withdrawn. The alumina crystallizes on the end, creating long carrot-shaped boules of large size, up to 400 millimeter in diameter and weighing up to 500 kilograms. The Krokowski method is best for its combination of good crystal quality, dimensional flexibility, and limited machining costs for overall value. The Kropolis method, or dip-and-turn method, is similar to the Krokowski method, but instead of pulling boule from the melt, this method directly crystallizes the melt by reducing the temperature. The sapphire takes on the shape of the melt chamber and produces large diameter boules of very high optical and high purity and low dislocation density. The boules can be cut into any orientation or plane. There are multiple horizontal moving growth methods. In general, a boat-shaped crucible moves through a fixed melting zone to produce large slabs or very thick windows. The material is very high optical quality, about grade 2 or 3, with nearly perfect edges in several crystallographic orientations, including C, M, or R plane. It's ideal for manufacturing sapphire blanks and windows with diameters from 2 to 8 inches and is used for blue LED substrates. With edge-defined film FED growth, or pull-through die method, a seed crystal is dipped into the melt on top of a die and pulled out for capillary action. The resulting shape is determined by the die. This method is good for creating various shapes and near-net growth, such as ribbons, tubes, and rods, and results in less machining costs. It yields low to medium optical quality and is commonly used for industrial, mechanical, and low-grade optical applications. The heat exchanger method, or HEM, is probably the most well-known to laymen because it was the method Apple was going to use to make their sapphire camera covers with GT advanced technologies. HEM is an inverted Kropolis method. It can produce very large boules of exceptional quality, but it is very costly. The Rotem temperature gradient technique is used to produce high-quality, near-net shaped domes for defense applications. For optical and other high-quality sapphire applications, sapphire must be grown as a single crystal. Sapphire is made up of many rhombohedral crystal units, which is the anisotropic hexagonal crystal we just learned about. For optical and high-quality applications, sapphire needs to be grown as a single crystal. That means that all submicroscopic individual crystal units, or grains, need to be lined up going the same way. No crystal growing method is perfect, and there are a lot of ways that a single crystal can go wrong. Think of the individual crystal units, or grains, as kernels of corn. If just one of those kernels is a little off, it can throw off the entire next row and the row below that. Dislocations are areas where the atoms are out of position in the crystal structure. Dislocations are generated and move when a stress is applied. Subgrain boundaries are low-angle boundaries present in material. When a grain is slightly out of location, it forms a small angle gap or boundary with its neighbors. Crystal lattice vacancies are when an atom is missing from its proper location in a crystal. The rest of the defects in this list also apply to glass: impurities, inclusions or embedded foreign material, cracking, and bubbles. In an ideal world, we'd have a perfect crystal with no defect. But perfection costs money, so we'll separate sapphire into grades to balance price and quality. Unfortunately, there is no single globally accepted grading system that is used by all manufacturers. Instead, synthetic sapphire is graded by what's most important for a particular application, be it optical or mechanical. Optical grades can be broken down into three main categories. High-grade sapphire has little or no light scatter and minimal lattice distortion. It's used for the most demanding optical applications. UV-grade sapphire is very pure, giving it both higher transmission in UV wavelengths and better resistance to solarization and darkening. Low-grade sapphire has extensive light scatter or lattice distortion, being used mainly for mechanical and structural uses such as bearings, fixtures, and less demanding optical applications. Here is an example of a grading scheme. Grades 1 through 4 are considered optical quality, while grades 5 through 6 are for technical or mechanical applications. In this particular example, bubbles are the primary grading designator. The comments about color on the bottom are an indicator of the level of impurities that are allowed. The price of raw material can vary dramatically between grades, with more than a 10 times price difference between mechanical and optical grades. Even within optical grades, we've found the same common sizes and formats, prices can differ by more than double. We've also found significant price variation across global regions, but also quality that is not as claimed. This is mostly a review of applications scattered so far throughout the presentation, but I'd like to review sapphire optical windows since this is a big part of what we make at IRD Glass. Sapphire windows are ideal for applications requiring high pressure resistance, high temperature, or high thermal loads. So they're good for vacuum applications or applications needing scratch and wear resistance, applications needing low friction, and applications with corrosive atmospheres. Sapphire windows are commonly used as protection window at the end of an optical system. Industries that use sapphire windows include research, medical, space, and aerospace, military and defense, and industrial manufacturing. Sapphire windows have a very wide optical transmission band from UV for high purity sapphire to mid-IR, about 150 nanometers to 5.5 microns. Sapphire is significantly stronger than other optical materials and standard glass windows. Or in other words, sapphire windows can be made much lighter and thinner than optical glass while maintaining the same strength and resistance to breaking. Sapphire has little to no UV radiation darkening when high purity, low defect quality is used. Sapphire growing techniques continue to improve, allowing larger part sizes and better material quality. These improvements also help bring down the price of sapphire and open up new application areas. Applications once dominated by Alon and spinel are now being replaced by sapphire because of the increased commercial availability and lower raw material costs. One application area enabled by larger sizes is sapphire windows for airplanes, UAVs, and other large viewports. For transmission up to mid-IR wavelengths, only zinc selenide and zinc sulfide were available in larger format windows. Both materials have a maximum strength of less than 100 megapascals. Because sapphire is so much stronger, it can provide the same strength with just a quarter of the thickness and no light scatter. For aerospace applications, this is especially important because it also cuts down on the weight. For armored applications, a glass sandwich with sapphire as the upper layer can provide a protection in a quarter or a third of the thickness of traditional armored glass. From an optical standpoint, viewports have many different light sources and detectors working at different wavelengths and require a broad transmission wavelength range. Zinc sulfide and zinc selenide do not transmit as well into the UV and visible spectrum as sapphire. For the most part, the applications I've gone over today are broad categories of sapphire uses. If you drill down within any of these applications, you'll find an entire world of uses. For this application highlight, I've chosen photodetectors and diodes. Sapphire windows are used in this application primarily for their broad optical transmission spectrum out to the mid-IR. Some applications may also take advantage of scratch resistance and chemical durability. For photodetectors and diodes, a sapphire window is hermetically sealed to a metal cap that is welded onto a photodiode package. The sapphire window usually has an additional anti-reflective or optical filter coating. I'm not going to go through the many applications of photodetectors and diodes listed here, but I do want to point out how wide-reaching they are. There are applications in research, medical diagnostics, environmental sensing, military, security, spectroscopy, and industrial manufacturing. I've also included a list of photodiodes and detector types that are likely to use sapphire windows. What you may not know is that sapphire might also be under the hood, so to speak, because lead sulfide can be grown on sapphire wafers. Many of these detector materials are grown on silicon wafers, which are processed using sapphire wafers as carriers. If you're looking for a custom sapphire window for your application, it's best to design for manufacturability when you can. Here are some common format cost drivers for sapphire window manufacturing. Flatness to aspect ratio. As mentioned earlier, sapphire can be made thinner than traditional glasses of the same diameter because it's stiffer and harder. Even though it's easier to make a larger aspect ratio with sapphire, it's not any easier to make it flat. Specifying a tight flatness with a large aspect ratio will increase costs. The size of clear aperture. A window is lapped and polished, the outer portions of the window loses material faster and become thinner. This is called edge roll-off. A clear aperture larger than 80% will drive up costs because edge roll-off needs to be addressed with specialized and often slow processing. A looser flatness surface quality spec will minimize the cost effect of a large clear aperture. Maximum edge chip. This can be designated as the size of a chip into a part, the total length of a chip, or the number of chips allowed. The smaller and fewer edge chips allowed, the higher the cost, as chipping is inherent and difficult to control. Thickness or thinness. As parts become thinner, they become more fragile, harder to fixture, and harder to handle. Sapphire is hard and strong, but is also very brittle. Thinner parts, especially R-plane, are easier to break during manufacturing. Square shapes are more difficult than rounds. Polishing is done in a circular motion, so a square or rectangle will have some portions of the part seeing slower speeds at the outside than the inside. Roll-off is also more severe at the corners of squares and rectangles. Overall size. At IRD Glass, our double-side polishing equipment is capped at 4 inches diameter, which is the best process to use if flatness or parallelism is important. Our single-side process can handle up to 10 inches. Every fabricator will have their own size limitations. But beyond the actual fabrication limitations, raw material pricing of optical quality sapphire is the largest cost driver for windows. A 4-inch window is really 6 times larger than a 1-inch window when you consider the material used. So the price will also be about 16 times larger. Sapphire usually costs more than other refractory materials. Costs are driven by both the raw material and the processing. Comparing pricing from a popular optical catalog house, we found that the price of 1-inch sapphire windows were approximately 1.5 times the price of fused silica and 2.5 times the price of BK7 windows. This price comparison is an estimate due to the slight variations in surface quality, flatness, and thickness of the listed catalog windows. Requesting a specific crystal orientation may add considerable cost, especially if it's less common or harder to fabricate. For example, M-plane takes considerably higher pressures and processing times than C-plane to lap and polish. The performance advantages of a particular crystal orientation should be weighed against the added cost and lead time. The maximum size of a sapphire product cannot exceed the largest spool that can be made or grown. Currently, that's about 36 inches for optical grade quality. Because sapphire is a grown material, the cost of larger sizes can be disproportionately higher than common sizes. Much like in the early days of silicon wafers, where 150 millimeter wafers was common, 200 millimeter was expensive, and 300 millimeter wafers were unheard of. Now, of course, most people are using 300 millimeter silicon wafers, and the prices have dropped considerably. Much the same, the price of large diameter sapphire, and sapphire overall, continues to drop as improvements are made in growing techniques and sapphire becomes more popular commercially. Making a raw material close to net side saves cost on both material waste and processing time. Because sapphire cannot be bent, molded, or drawn like glasses and metals, some shapes are very inefficient. For example, glass domes can be made by heating and vacuum slumping glass or molding, which cannot be done with sapphire. Thankfully, there is a special growing technique to make domes for sapphire, but you get the idea. Fused quartz or other glasses are superior for thermal insulating. On the other hand, sapphire is a great thermal conductor. Because of the larger expansion coefficient, larger pieces of sapphire can be thermally shocked and broken if not heated uniformly. And finally, sapphire is brittle. I hope this presentation made you excited to try sapphire for your next project. If you're interested in learning more about sapphire, I highly encourage you to buy Sapphire Material Manufacturing and Applications by Elena Drobovinskaya and published by Springer. There is even a teaser chapter available on Springer's website. I didn't write this book, and I'm not getting any commissions from it. Elena, if you're listening, I'd be happy to take commissions. I'm just joking. But I think this is a really excellent book on the subject and delves into a lot of detail that we glossed over today. It even has detailed information about lapping and polishing for those of you planning to fabricate sapphire yourselves. Thank you all for your time today. That concludes my presentation, and we'll now open the talk to questions.
And thank you very, very much, Michelle. And thank you for the amusing picture here of the cat with his glasses on. And at this time, if attendees have additional questions, please add them into the question box. And I will be sure that Michelle receives all of your questions and all of your contact information and has the ability to answer you offline. Michelle, several of the questions were answered by Todd while you were going through your presentation. If you would like more information, attendees, about Sapphire, please contact Michelle DeCastro at the information you see on your screen. And at this time, I'm going to close the webinar. A recording will be available shortly, and you will receive links to the recording in a note tomorrow. I would like to thank our presenter, Michelle DeCastro, IRD Glass, and all of you for participating in today's webinar hosted by Photonics Media.